Users across the workspace see connecting indefinitely. WebSocket handshake latency spikes from 50 ms to 30 seconds. The channel server's memory grows until the OOM killer intervenes. The root cause? A 10x fanout amplification from Redis pub/sub. Let's break down why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover design slack. Design slack means sizing connection pools, thread pools, and queue depths to handle 3-5x expected peak. It decouples components so a slow consumer doesn't stall the entire pipeline. Slack maintains millions of WebSocket connections. Each server subscribes only to channels that have local users, reducing Redis subscription overhead by up to 50x. Here's the connection server code. It maintains a map of user IDs to WebSocket connections and broadcasts messages only to users in the target channel. If the handshake handler is single-threaded, a burst of new connections blocks the event loop, delaying heartbeats and message delivery for already connected users. Always isolate handshakes in a separate thread pool. When a user sends a message, the server publishes to Redis pub/sub. All servers with subscribers receive it and forward to local connections. This creates n reads per message, where n is the number of servers. The Fanout service publishes to Redis for live delivery and to Kafka for async processing like offline catch-up and search indexing. This decouples the real-time path from background tasks. Messages are stored in Cassandra with a composite key of channeled and day bucket to spread writes. Cursor-based catch-up avoids full scans, and local quorum ensures strong consistency for recent messages. The schema uses channeled and day bucket as partition key to spread writes across partitions. The TTL automatically deletes messages after 90 days, avoiding Tombstone accumulation. Read replicas can lag 500 ms behind the primary, causing users to see missing messages or stale reactions. Always route recent queries to a strongly consistent store. Route queries by time. Recent messages go to a strongly consistent Cassandra ring, older messages to blob storage. This avoids replica lag for the critical recent history. Presence uses heartbeats every 15 seconds with adaptive intervals. Idle users send every 60 seconds, active users every 5 seconds. Updates are debounced to avoid flooding clients. The presence service maintains a map of user IDs to last heartbeat timestamps. A scheduled task runs every 30 seconds to remove stale entries and publish changes. Using a per-channel debounce window caused all presence updates to be delayed when a user's presence flapped across channels. The fix is to use a per-user sliding window instead. Search indexing is decoupled from the real-time path. Messages are published to Kafka, and a consumer indexes them into Elasticsearch. Recent messages are merged from Cassandra to hide indexing delay. The search indexer consumes messages from Kafka and indexes them into Elasticsearch. Using the idempotency key as document ID ensures idempotent indexing. File uploads are isolated from message delivery. Files are stored in a staging bucket, scanned for malware, then moved to a public bucket. Thumbnails are generated after scanning passes. The upload handler rejects oversized files early, stores the file in a staging bucket, and queues it for scanning. This prevents malicious files from being served before scanning. Offline users rely on push notifications, but they are unreliable, only 85% delivery on congested networks. The solution is a client-side cursor that syncs only new messages on reconnection. On reconnection, the client sends its cursor. The server returns only messages after that cursor, deduplicating by message ID. This saves 99.6% bandwidth compared to resending the entire channel. This is the same issue we highlighted at the start. Here's exactly why that happened. A reconnection storm hit the single-threaded handshake handler, blocking the event loop. Subscription counts spiked 5x, and Redis pub/sub amplified each message to all servers, causing OOM. The fix: isolate handshakes in a dedicated thread pool so the event loop stays free. Implement subscription budgets to reject new subscriptions when overloaded. Use connection draining to spread reconnections over 10 seconds. Without a subscription budget, a server crash causes all reconnecting users to subscribe to channels, spiking subscription count 5x. This amplifies fanout and leads to OOM. The article mentions subscription budgets but doesn't show how to enforce them. Here's a concrete implementation that rejects new channel subscriptions when the budget is exceeded, returning a try-again signal to the client. Redis pub/sub channels hold messages in memory until all subscribers consume them. If a subscriber is slow or disconnected, messages accumulate, potentially causing Redis to run out of memory. Always set client output buffer limit for pub/sub clients and monitor memory usage. Slack uses a dedicated Redis instance for pub/sub to avoid evicting cache data. The article describes adaptive heartbeat intervals but doesn't show the logic. Here's a simple implementation that adjusts the interval based on user activity, reducing server load during idle periods. The article warns about Tombstone accumulation but doesn't mention monitoring. In production, you must track Tombstone counts per partition. Use NodeTool stats to check SS table count and max Tombstone per slice. Set alerts when tombstones exceed 100,000 per partition to avoid read timeouts. Slack uses a background compaction job that runs during low traffic to merge SS tables and reclaim space. To diagnose fanout issues, monitor pending handshake count, subscription count per server, and Redis pub/sub reads. Alert on Kafka consumer lag to catch indexing delays early. Let's run through some common interview questions. How does Slack handle WebSocket connection storms, dedicated thread pool, subscription budgets, connection draining? Explain the fanout amplification problem. Each message is read n times, n equals servers with subscribers, causing O(n) load. How does Slack ensure offline users don't miss messages? Client-side cursor with delta sync on reconnection. And a few frequently asked questions. What is design Slack? Structural buffer that decouples producers from slow consumers. Why not use push notifications for offline delivery? Push is unreliable 85% delivery. Use cursor-based sync instead. How does Slack avoid hot partitions in Cassandra? Time-bucketed row keys, channeled plus day bucket, spread writes. To recap, design Slack decouples components, fanout amplification is the real bottleneck, and always plan for connection storms with budgets and draining. Ready to go deeper? Up next, design a rate limiter, then design a notification system, then design a search autocomplete. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.